I think it's time to start with this oral session after this very good meal we have had, and I think it's a perfect moment to make the digestion, enjoying with this two nice presentation. My name is Alejandro Rodriguez, and I'm the chairman of this session. And let's start with Fabio, with the speech of Fabio, which holds a PhD in chemical and biological engineering from the Faculty of Engineering of the University of Porto. He's currently a researcher at CISECO, University of Aveiro, working on the bioeconomy for textile and clothing project. His work focuses on the use of lignin in the development of regenerated cellulosic fibers with functional properties for textile application, as well as the functional modification of non-woven fabrics. Fabio, the floor is yours.
Thank you very much. Good afternoon, everyone. My name is Fábio Bernardo, and I'm here representing the University of Aveiro, more specifically the CISECO Associated Laboratory. I would first like to thank the organization for the opportunity to present our work here at Tecnicelpa. As you can see by the title, I'm going to talk to you about lignin-modified lyocell nonwovens, a path towards sustainable textiles with hydrophobic properties. This work was done as a collaboration with University of Aveiro, Altri, and also CITEV. Here I present a brief overview of the presentation. I will start by a brief introduction, giving you a brief context regarding the BEAT project. Then we'll move on to the research methodology, how we modify our nonwovens, the main results, and finally the conclusions. So, to give you a brief context, our work that we'll present here was done under the BEAT project, which is a large-scale initiative that aims to accelerate the transition from fossil-based to bio-based materials in both clothing and textile industry, representing an investment of around 138 million euros. It is led by CITEV, which brings together a total of 58 entities, of which 21 are research and innovation institutions. So as you can see, it's a really big project. It started in 2022, and it will end next year in 2026. Here we highlight the institutions that we work as University of Aveiro closely with, CITEV, CENTI, and from Altri Group, CAIMA, and also CELBI. So I would like to do the introduction in three separate components. First of all, giving you a brief idea of the textile industry. As you know, in the recent decades, there's been a growing concern regarding the acquisition or development of more natural and sustainable fibers for several reasons. For example, environmental concerns. We all know about climate change, the release of microplastics from synthetic fibers to the ocean, also the large quantities of fast fashion waste that ends in the landfills, and so this is the first reason. Second of all, the increased awareness of our consumers. Also, sustainability-driven goals of the companies. And finally, some regulatory pressures, for example, to include recycled material in our textiles. Here specifically, we're going to talk about nonwovens. So they are not knitted or woven, but they are bonded using several methods. Before that bonding, we have a web formation that can be wet laid, dry laid. It can be different strategies. And then the bonding can be mechanical, for example, needle punch, where we entangle the fibers. It can be also thermally, for example, spun-bound nonwovens, and also chemically using some adhesives. The problem with these nonwovens is that they are mainly produced using synthetic fibers such as polyester, polypropylene, polyamide. So we wanted to take a different approach, using more sustainable fibers. In this case, we opt for LYOCELL. For those of you who don't know this material, basically they are a regenerated cellulose fiber that is made from wood pulp, more specifically dissolving-grade wood pulp, that we dissolve in a solvent called NMMO, and then we extrude through a spinneret and regenerate in water baths. So the LYOCELL provides a unique combination of technical performance, sustainability, and also comfort. And then our third component, our additive, in this case, We use KRAFT lignin provided by Alti Group, which is a byproduct of the wood pulp industry that is often underutilized. It's mostly burned for energy recovery. So we want to use this that was purified via the lignobus process to see if we could impart some interesting properties in our nonwovens. So our three main goals were, first of all, to develop nonwovens and modify them with the KRAFT lignin, see how this modification will change the physical properties of our materials, and also, for example, if you could obtain hydrophobicity, UV blocking properties, or other type of properties. To finally assess if the KRAFT lignin indeed presents a potential as a sustainable additive to textile application in the context of circular economy. So we are using a residue from a wood pulp as a resource for the textile industry. So moving on to the modification process, in our case we use needle punch nonwovens, so they are produced mechanically by entangling the fibers. And we start by impregnating them in lignin solutions that were prepared in ammonium solutions, followed by the padding in a fuller machine, which is basically two rolls that compress our sample, and then where the magic happens, which is the hot press at different temperatures. In terms of analysis, we divide them into three groups. First, the surface and morphology. We assess the water contact angle, also some SEM and FTIR. In terms of chemical analysis, we did elemental analysis and lignin uptake by extraction with sodium hydroxide. And then in terms of functional and durability, we assess the wasting fastness with successive washings, and also UV blocking and tensile tests. Here I present to you the samples that we obtained using three different concentrations. As you can see, the unmodified sample was white, which is the normal color of LYOCELL, and as we increase the concentration of lignin, we get different shades of brown, increasing with the concentration of lignin. These images were obtained with a digital microscope, and we only present the hot pressing at 180 degrees because all the samples, independently of the hot pressure, present the same colors. If any of you want to see the samples live, I have them here with me, so you can talk with me during the rest of the event. Moving on to the water contact angle. First, in this slide, we want to assess what was the ideal hot pressing temperature and why. Initially, we didn't include the hot pressing in our procedure, but even by adding the lignin, we couldn't obtain hydrophobicity. So we started thinking, what can we do? Is there any process that is already used in industry that we can apply? And we thought of the hot processing. In this case, we tested three different temperatures with these several measurements. And as you can see, with 130 and 150 degrees, we could obtain very stable results. Sometimes it worked, sometimes it didn't. But when you use 180 degrees, as you can see, almost up to 100 seconds, around 130 degrees of water contact angle. So it's clearly hydrophobic. But how can I explain this? Why at 180 degrees it works? Well, we believe that it's due to a lignin glass transition temperature. We assessed using DSC, and it was around 143, 145. So clearly 130 was below, 150 was slightly above, but it might not still provide the property we wanted. And with 180, you have the compression at 2 bar of the hot press with the heating, which means that the bondings between the hydroxyl groups of the cellulose fibers will interact better with the lignin because it's more malleable, so providing a hydrophobic surface, uniform surface on our material. So according to our results, 180 degrees seems to be the optimal temperature. In this next slide, so we want to set how much lignin do we need, because if we want to translate this into an industrial process, we want to have an efficient process. We don't want to waste any money on unnecessary resources. So what we did, we assessed the contact angle with 5, 25, and 100 grams per liter. You can see clearly that it's hydrophobic and it's very stable. But after 10 successive washes, only the intermediate concentration work, which is interesting. But how can you explain this? Basically, 5 grams per liter can probably be removed after 1 or 2 washes. It's simply too low concentration. And at 100 grams per liter, we're using excessive lignin that simply does not interact with the cellulose fiber. There's only an amount of interaction that can happen between the fiber and the lignin. So we are basically wasting it. And during the turbulence of the washings, you can expose the hydrophilic parts of the material. So according to these results, the optimal lignin concentration seems to be the intermediate one, with 25 grams per liter. Moving on to the lignin uptake, we know our samples, how much sample we use, we know the uptake of our sample, so we can determine the theoretical value that we might obtain with our samples. But to really know how much lignin it absorbs, use lignin extraction with 5% sodium hydroxide, followed by lignin precipitation and centrifugation. And as you can see, when you use 100 grams per liter, we have almost 50% losses. So we are basically using lignin for nothing. It doesn't interact with our material. However, with 25, only around 5%. So we believe this is the optimal point in our process. And with 5%, it was just such a small concentration that we didn't even measure. So according to these results, once again, the intermediate concentration seems to be the most appropriate one, the better in terms of properties. We also want to assess visually, not only visually, but with the same imaging, how the lignin will be distributed in our nonwovens. As you can see here on the left, the unmodified nonwoven presents the classical structure of LYOCELL, which is clear, round surface. And when we add the highest concentration of lignin, you can clearly see some deposits on the surface, and possibly even in the interior of our material. Of course, as we increase the lignin, the samples become more viscous, so it might have a harder time penetrating inside the material. Another test that we did was the ATR results to assess also if we indeed modify the nonwoven in the surface. As you can see here in these two identified bands, we identified some bands associated with lignin, aromatic skeletal vibration, double C bonds. However, they were more noticeable only in the highest concentration, but this can be due to a limitation of the equipment itself, because ATR only probes the tops 0.5 to 2 microns of our material. Moving on to the elemental analysis, we only present here the carbon and hydrogen results because our lignin and our nonwoven didn't present any nitrogen or sulfur. But as you can see here, as we add more concentration in our solutions, we have almost a perfect linear correlation with percentage of carbon. So it's an indication that we are successfully modifying our nonwovens. Then the test of washing, successive washings. In this case, we measure the color intensity values and also the CLab color coordinates, although we do not present them here. And as you can see, the more lignin we add, the higher the KS value. But we can see for the highest concentration, a sharp decrease in the color intensity, an intermediate decrease in the intermediate one, and thus a low decrease in the lowest concentration. Of course, it will depend on the application of our nonwovens. If we use them, for example, for geotextiles, it's going to be under the terrain, so we don't care if the material gets clear or not. So it depends on the application. But for other cases, it might be relevant. Then for properties, in terms of UV blocking, we assess using the norm presented here, using UV near spectrophotometer. And as you can see here, in the transmittance graph, in the control group, it went almost up to 20%, but as we add more and more lignin, it reduced almost to 0, which clearly affects the ultraviolet protection value, which changed from 33 to 50 plus, which is considered excellent protection against UV. And how can we explain these results? Of course, due to the lignin that we have. For example, due to absorption, since it has carbonyl groups in this constitution. Also some antioxidant effects due to the phenolic compounds, phenolic groups in the lignin, for example, that can neutralize free radicals and prevent photochemical degradation. And also due to the branch and amorphous structure of the lignin, it can also have some reflection or light scattering. We also did some tensile strengths here, according to this norm, which basically assessed the ultimate tensile strength and maximum elongation in the machine direction of the nonwoven. Once again, we did needle punch nonwovens, and also in the cross direction, so in the length and in the width. And as you can see here, When we add only 5 grams per liter, the ultimate tensile strength remains basically the same at 400, but when we add the intermediate concentration, it jumps to almost 500 newtons, although the maximum elongation is constantly decreasing. On the width direction, the ultimate tensile strength is much lower, it's around 100, but the elongation also sharply decreases. So we have an anisotropic behavior, which is typical of non-wovens, and because they are stronger in their machine direction, and of course with the hot pressing, we also contribute to this phenomena. So we can say that lignin makes our samples a little bit stiffer, but also less elastic. And once again, the intermediate concentration seems to be the ideal point. So in terms of conclusions, we can say that we successfully modified our nonwovens, and we can change the color of our assemblies by adding lignin. We also develop a sustainable approach that imparts not only color, but also hydrophobic and UV blocking properties. And I can tell you that we also did some extra tests, and we are also obtaining good results in terms of antimicrobial and thermal properties. So we need to develop that area a little bit further. And so, yes, we can say that lignin presents a potential as a multifunctional bio-based additive to improve the performance of our nonwovens. Of course, it will depend on the type of applications. Are we talking more of geotextiles? Are we talking more about construction insulation? Are we talking about temporary pots for plants to transport? So there's a wide variety of applications. I would like to thank the financial support, also Altri, CITEV, and the University of Aveiro, because these results will not be possible without their collaboration, and all of you for your very kind attention. Thank you very much.
Thank you, Fabio. You speak quick. I really don't know how you can breathe, so it's the time to Micaela. Micaela is a master in chemical engineering from the University of Aveiro and a postgraduate in industrial economics and management. She started her career at Selby as lab technician, then process engineering, being currently part of the Altri Group's innovation team. Currently, she is a PhD student in chemical engineering at the University of Aveiro, focusing on novel application for KRAFT lignin, published 2 articles in peer-reviewed journals related to her PhD work. So, Micaela, the floor is yours.
Okay. Thank you. Thank you for your words. And good afternoon, everyone. So I'm here to present this work, which is part of my PhD project, and we'll talk a little bit about lignin carboxymethylation. Just making an overview of today's presentation, I will start by a brief introduction to lignin and lignin functionalization, focusing on carboxymethylation, experimental setup, key results, and conclusions. So, as you know, lignin is a major byproduct of the pulp and paper industry. It's recovered mostly by the KRAFT process and primarily burned for energy producing. But this amazing biopolymer has potential for being valorized into new biochemicals or functional materials. However, its complex structure may limit its valorization. It has low reactivity, and for attain specific properties for specific applications, functionalization may need to be attained. So, for several functionalization methods, we focused on carboxymethylation. This functionalization enhances lignin solubility, chelation capacity, and surfactant behavior, making this material suitable for materials like dispersants or biosorbents. Regarding this reaction between lignin and sodium chloroacetate, this occurs via a nucleophilic substitution mechanism where phenolic hydroxyl groups are the most reactive. They are easier due to their easier ionization in alkaline conditions, and the aliphatic hydroxyl groups, they are less reactive, and we don't know for sure at which extent they react. Also, during this reaction, also sodium chloride and glycolic acid are formed as byproducts. This reaction It strongly depends on the sodium chloroacetate to lignin molar ratio, the sodium hydroxide concentrations, and temperature and the reaction time. The main goal of this work was to assess the optimized conditions for this carboxymethylation, to have a detailed characterization of the modified lignin, as well as the substitution patterns of these new carboxymethyl groups, and to assess the ion exchange capacity towards transition metals. To do so, we use an eucalyptus KRAFT lignin, which was isolated by the LIGNIN-MODIFIED process, and it was previously characterized. Lignin carboxymethylation occurred under alkaline conditions, and we focus on optimizing 4 key parameters: temperature, time of the reaction, sodium hydroxide concentration, and sodium chloroacetate to lignin molar ratio. After each reaction, we measured the degree of substitution using a potentiometric titration using methods already described on literature. Having those optimized conditions, they were applied at the pilot scale to prove if it's scalable and the repeatability of this process, and the modified lignin was further characterized by elemental analysis, thin analysis, and other analysis. And also we also try to understand this metal sorption behavior of this modified lignin in comparison to the pristine lignin, focusing on cadmium, copper, and mercury ions. So, starting by the lab scale experiments, we observed that the maximum degree of substitution was attained at 60 degrees. We also observed that higher sodium chloroacetate concentrations resulted in a higher degree of substitutions. We don't see significant differences between degrees of substitution in different reaction times. And medium sodium hydroxide concentrations resulted in higher degree of substitution. So the optimal degree of substitution was attained at a temperature of 60 degrees with a molar ratio of sodium chloroacetate to KRAFT lignin of 3, sodium hydroxide concentration of 1.5 molar, and a reaction time of 2 hours. Those conditions were applied at the pilot scale, and the obtained modified KRAFT lignin showed a degree of substitution of 0.41, which was slightly lower than the obtained at the lab scale, which was about 0.45, but within the reported range of values. Elemental analysis was performed to have this, to calculate this new empirical formula of phenylpropane units, where you can see these new carboxymethyl groups in here. But, okay, we have these new groups, but we also observed that the molecular weight is lower in the modified lignin. And this occurs due to the polymerization of lignin under strong alkaline conditions. Further analysis also comproved these new carboxymethyl groups. We observed that there is an increase in stretching in the carbonyl bonds for both carboxyl and carboxylate groups, and a decrease in stretching in the hydroxyl bonds for the carboxymethylated KRAFT lignin. We also analyzed the proton and carbon NMRs, and regarding the proton NMRs, we observed that new signals appear for the carboxymethylated KRAFT lignin at this red band, which are associated to the methylene protons in carboxymethylene phenyl ethers. Additionally, increased resonances at this orange band, which indicate the presence of methylene protons in carboxymethylene alkyl ethers. Quantitative analysis using phenolic methoxyl groups as internal standard showed that we have a decrease in the phenolic hydroxyls in about 40% and in aliphatic hydroxyls in about 80%. Regarding the carbon NMR, new signals from carboxyl and methylene carbons appear at this yellow and green band. And we also see an increase in the resonance at 152 ppm in here. which confirm the etherification of phenolic hydroxyl groups during the carboxymethylation process. So, this seems complex, but it's not. We also, to gain deeper insight into the substitution patterns of these new carboxymethyl groups into the modified lignin, we employed single bond proton-carbon correlation spectroscopy. In the graph, we see the spectra of the modified lignin in red, superimposed of the pristine lignin in gray, so the red is above it. And in here, we observe that new cross signals appear. Are you seeing this? Appear within the spectral range in here that belongs to the methylene carbons in carboxyl moieties and the esterified methylol in both syringyl and guaiacyl units. But this analysis also showed that some esters form at the methylol position, at the gamma carbon, and some ethers forms at the benzylic position at the alpha carbon. And those structures were not being yet described on literature. So the aliphatic hydroxyl groups do react. Regarding aromatic region, we observed that for the carboxymethylated KRAFT lignin, some steel band structures appear in the carboxymethylated KRAFT lignin, which are formed during the strong alkaline conditions of the reaction. Regarding this ester formation, which was not described, we suppose that it forms via benzylic esters of glycolic acid, which migrate through amystyl intermediate to form a more stable adduct. And this occurs during the acidification step to precipitate lignin. We also performed thermogravimetric analysis of these two composts, and the maximum, they have similar behavior, but the maximum degradation rate occurred for the modified lignin a little bit at lower temperatures, more or less 50 degrees. And we also observed that the modified lignin shows high ash content. And this is due to the presence of carboxyl groups in the form of sodium salts. So, during this presentation, we have talked about the introduction of these carboxymethyl groups into the KRAFT lignin, and these carbonyls or carboxyl groups in this modified lignin are strongly related with the chelation capacity of this lignin. To improve these abilities, tests were conducted in a batch mode using low concentrations of copper, cadmium, and mercury solutions in the order of 10 under the power of -5 molar, which is really low concentrations. And we use such low concentrations because they are corresponded to the minimum emission values. We observed that, of course, KRAFT lignin has some carbonyl groups, some hydroxyl groups, and they have some sorption capacity, but this modification strongly improve this chelation capacity. For example, for copper and for mercury, we observed that this modification resulted in higher uptakes, and the equilibrium time was attained at a faster time. So you have faster equilibrium time for the carboxymethylated KRAFT lignin. Regarding cadmium, the uptake for the modified KRAFT lignin was 7 times higher than for the unmodified lignin, but it has some time to reach the equilibrium. So, we have learned that these lignins may have potential for being used in wastewater treatments, not as is, but they have this potential. But they can have potential to be used in other applications. They can be used, for example, in bioremediation or biostimulation, for example, in control release of pesticides or plant growth stimulation. And this helps mitigate both ecological and toxicological risks, benefiting both agriculture and the environment. In addition, this modified lignin can have also some more industrial or usual applications, such as a bio-based adhesive for MDF or other wood products. And in here, I show a simple experiment that we have done. We have solubilized the carboxymethylated KRAFT lignin in ammonia and mixed it with the refined pine fibers, and we obtained an MDF board with properties similar to the ones that we have with phenol formaldehyde resins. This lignin, or this new product with this lignin, have improved the properties since this lignin improves mold resistance, flame retardancy, and water resistance. This said, I think we have all these applications for lignin and for this modified lignin. We can say that this is a sustainable and a high-performance alternative for new materials and for new uses, applications. Just making some conclusions, we learned during today's presentation that this reaction can be scalable, that the most of the hydroxyl groups involved in this carboxymethylation reaction are the phenolic ones. It occurred a side reaction at the gamma carbon, forming an ester, and of course this lignin improves the chelation capacity towards transition metals, mostly for cadmium and for the others too. Next steps for our work will focus on immobilizing this lignin into inorganic and organic matrices. We will want to try different lignins from different eucalyptus species. And of course, we want to study new application areas for the carboxymethylated KRAFT lignin. To finish, I would like to thank Selvi for supporting my PhD project, XXVII and Sessão, my professor and my colleagues for their collaboration, and thank you all for your attention.
Okay, thank you, Micaela. Because Fabio and Micaela were on time, we have time for at least 1, 2, or even 3 questions from the audience. Some question, they explain very well, but you know, some curious, something like that. Okay, I have the same question for both. I want to know your opinion about how close do you think are these processes to be applied at an industrial scale. You explain you are pilot scale, but you know, the following step.
Yes, so regarding this, are you listening to me? No? Yes. Yeah. No. No, yes. So regarding this specific application for carboxymethylated for lignin, what can I say? We proved that this is scalable, and the process is quite similar to the one that we have for carboxymethylated cellulose. So, which is an already established process. The process, the conditions, the reagents are the same. So, I think it might be easier to scale up since that similarities. But regarding the lignin itself, I don't know if you are ready yet, if the market is ready yet to have these new materials. But this work, I think these works are important to prove that, okay, these new bioproducts have potential for new applications, and we have to also call for the market, okay, listen to us and see what we are doing with these new materials.
Thank you very much. I agree with Micaela. In our case with the nonwovens, we thought of this process of scaling up to the industrial level already. When we thought about the hot press, it's already used for the production of the nonwovens. Of course, we focus here more on the needle punch nonwovens, but there are other types of them, spunbound,
hydrotangling. Of course, each process affects the type of non-woven you obtain. For example, the face masks we use during the COVID, it's non-woven. The bags we carry, our suits, for example, that's non-woven. So it's used in a different type of applications. We use needle punch, the needle punch version because it's more appropriate to technical applications. So for example, geotextiles, construction insulation, maybe filters, I don't know. So, and with the addition of lignin, of course, you're going to get a more premium product. It might be more expensive than the standard version, just LYOCELL, but you don't have the benefits, the UV blocking, you don't have the hydrophobicity. So I think, as Micaela said, we need to talk with the companies and ask, what do you need? What type of application would you find this is more suitable to? And can we find a matching ground in between so we can help you obtain what you want, the type of products? Of course, always searching for environmental concerns, but also the economical component. That's very important. But I believe we are close to getting the market. We just need to talk with the companies and convince them and bring them together to join the boat.
Okay, good news. Okay, so thank you. Again, Fabio, sorry, mix the name, Micaela, and thank you all of us for being here. The next session is Forest with Luis Leal from Altri as chairman, and I remind you, take a look in the cell phone app, you will find important information. Thank you.